Welcome to Ask and Learn.
In this problem, we are given a linearly decreasing load density between some unknown density force downward of W naught at one end, and at the opposite end there is an 800 pounds per foot force density value. We are asked to find the reaction force at supports A and B given their location along the beam at 5 feet from left and 12 feet from left, or the span between them is 7 feet. Later, we're given that, or this program also gives us the value for W sub naught, our force density value at the extreme left-hand side of the beam. We're given a value of 400 pounds per foot. The approach we're going to use to solve for these reaction forces at each of the supports is to first write out the load density, this linearly varying relationship, as a function of the beam coordinate x, that's the span from the leftmost point, and in terms of the arbitrary parameter that we are given, but for the next problem, it's better that we keep it arbitrary as long as we can. This parameter we will symbolically represent as W sub naught. Next, we'll integrate that function to find the total load, integrated over the span coordinate x, to find the total load that we'll denote here as F total. And it's going to be pointing downward from the load. The reaction has to exactly oppose that. And we will also calculate the centroid location on the beam using the function we derived in step 1. Finally, we will insert the specific value we're given of 400 pounds per foot for W naught, and then we'll solve for the reaction forces at each of the supports using the usual statics equations that were given. If something is static, it cannot move linearly in space. It can't have any translation. So the opposing forces of the supports, the sum of those forces will exactly cancel the total force of the load. And the other thing is, since it's not rotating in space, the torques about the centroid must be equal and opposite. So this total torque is equal to 0. So for step 1, again, we're going to write out an equation for our load density relationship, load density function along the span of x. We have our endpoint at 800 pounds per foot. We have our starting point as W sub naught. So we're going to subtract, and that should be set. My apologies. I just double-checked the problem, and I miswrote the value here. It's not 800 pounds per foot. It is 300, as is correctly stated in my equation. Fix that real quick. Sorry about that. So going back to our derivation of the force density equation, we have 300, the y-coordinate at the final location, minus W sub naught, the y-coordinate at the initial location, over run of 12 feet, so a total of 12. That's our slope. Then for a linear equation, we multiply the slope by our dependent or independent variable x, and then we add the offset, and the offset is at x equals 0. We're given a value of W sub naught for our offset. Thus, we have our equation for the load density over the span of x, our dependent variable here. Next step is to integrate over the span of x in order to get the total load. So we have our equation just derived above as a function of x times the infinitesimal dx that we sum over the span, perform the integration. We're integrating from 0 to 12, the total span of the beam. Our independent variable x goes to x squared over 2. Rather, that was x dx goes to x squared over 2, and w sub naught dx goes to wx. We evaluate from 0 to 12, and we are left with this equation for our total load in terms of W sub naught. Secondly, we can find the centroid by this time integrating the product of our x coordinate times our force density function, and then our infinitesimal dx, performing that integration, evaluating from 0 to 12. And I'm sorry, I went too fast there. That numerator, the integration of the product of xw sub x dx, is over our total load, which we just calculated or worked out in the step above. So evaluating our numerator, we have 300 minus w sub naught over 12 times x cubed over 3 plus w sub naught x squared over 2. That numerator, both terms evaluated from 0 to 12, and then dividing by our total load relationship below. This can be expressed as follows here. Okay, our step 3, we will use those two equations from statics. Forces must sum to the total load, the reaction forces that is, and the torques must sum to 0. The magnitude of the total load by plugging in a W sub naught of 400 pounds per foot. If you plug that into this equation here, you should get 4,200 pounds for our total load. We also know that it's not rotating in space, so the opposing torques must exactly cancel each other. And that should be a 0 there. So we can work out the torques about the centroid at support B as follows. Looking back at our diagram here, wherever the centroid is, x sub total, it's going to be, the moment arm about it will be its location, x total, minus the location of support A, which is 5 feet. Or rather, the other way around, 5 feet minus the location of x total. And because we don't really know yet where this centroid lies, I'm going to make my life much easier with sign conventions and just multiply the force at FB by the absolute value of that moment arm. And I'm going to call the direction of that force negative. So that's for our first term, the torque about the centroid exerted by reaction force B. We do the same thing for reaction force C. It's located at 12 feet from extreme left. We have that 12 feet, and you subtract the location of the centroid, of which we don't yet know, so we'll keep symbolically. That moment arm will be 12 minus x total, location of the centroid. we will take its absolute value for that moment arm and say that that torque is in the positive direction. Here we are. Sorry, cursor's in the wrong place. And that moment arm times the reaction force at support C is expressed as follows. Those two torques are equal and opposing. So given the sum of the forces and the sum of the torques, we can solve now for the location of our centroid as well as the reaction forces. So we can find the value of the centroid by plugging in W sub naught equals 400. We do that in this equation here for x total, and we find that it works out to 5.714 feet. That would lie very close to this A support. It would probably be a little bit, probably in the neighborhood about right here. Now that we have a numerical value for the location of our centroid, we can plug that in to our sum of torques equation here, which I'm gonna underline this because it's a very important equation for this problem. So we want to draw our attention back to that. So given this, and given that we now know the location of the centroid, we can solve, use these two equations to solve the for both FC and FB, depending upon which one we subtract from and insert into our torque equation. Here I've solved for FC, and it comes out as follows. The value of the difference between the location of location of support B, which is at 5, minus the centroid, and that's divided by this denominator, which is the sum of the two moment arms about the centroid. That works out to, and that entire proportion is multiplied by the total load, and it's going to go in the opposite direction of the total load. So right now, to keep track of things, I'm going to put an upward arrow because the total load was pointing downward. Our forces must be in opposite directions. Working out those numbers, we have 428 newtons in the upward direction for the reaction force at support C. That we expect to be a lot smaller than the total load because if the centroid's here, the torque is exerted across a long moment arm, so the force doesn't nearly have to be as great here to oppose a force that is close to the centroid, a short moment arm at here. And apologize, but my I used the wrong values here for the supports. So let's fix that while we can. These should be B. This should be C. My apologies again. And I see that I made the same mistake here. Let's put these proper. That was the torque about supports B and the torque about support C. Okay, back to where we were. Likewise, we can the reaction force at support B is the same denominator, but the numerator is now the other portion of the span that goes the longer moment arm of the two in the numerator times the same denominator, which is the sum of the two moment arms, times that whole proportion times the magnitude of the total load, and the direction of the reaction force will be upward. you plug in the numbers for that. Remember, our value for x total was 5.714 feet. Plug in the numbers for our centroid location there, and you should have 3,772 newtons upward. And that concludes our problem. Let me box it. There we go.